Alright, welcome back to Math 1720, Chapter 5, Section 2. We're going to be verifying trig identities. So let's get right into it here. Alright, so the basic thing for you guys is to have your little identity sheet next to you. Alright, that will come in very handy when you're doing this. Alright, so what we're going to be doing is we're going to make one side look like the other. So whenever you see, I'm going to read this part verbatim here just so you get it. Whenever you see either side of a fundamental identity, the other side should also come to mind. Also, beware of the equivalent forms of fundamental identities. That means you're on the lookout for rewriting cosine squared as 1 minus sine squared, something along those lines. Rewriting like the Pythagorean, or recognize, oh, I got sine squared plus cosine squared, that's 1. Okay, so try to always choose the more complicated side to make it look like the simpler side. It's harder to go from simple to complicated than it is to go from complicated to simple when you do these. Alright, so try to get everything as best you can into terms of sine and cosine, and then simplify it. Alright, and make sure that we are handling all the algebra. So lots of kind of fractions and quotient type rules are going to apply here. Alright, so basically we can see that this is what the sum of sine x plus 1. This is how we can factor it down. So always look to simplify because it might translate into something else that can cancel for us. Alright, so let's take a look at another one here. Basic math rules. Sorry, there are little boxes on here. It got lost in translation and somehow it's not letting me edit. Those should be multiplication, so it should say 1 times cosine of theta, 1 times sine of theta there in the numerator. Alright, but it's a matter of you being able to do the algebra and combine fractions here. So we have 1 over sine theta plus 1 over cosine theta. Alright, we have to get a common denominator. So you're going to multiply the left-hand side. 1 plus sine of theta is going to get multiplied by cosine of theta over cosine of theta. And then on the right-hand side, the 1 over cosine theta, I'm still looking at the function on the left-hand side though, even though I'm saying right-hand side. The 1 over cosine theta gets multiplied by sine of theta over sine of theta. Because the denominator, okay, there's not a common denominator, so the only way to get the denominator is to multiply sine times cosine. So when you do that, alright, you're going to end up with 1 times cosine of theta plus 1 times sine of theta all over sine theta cosine theta, so we end up with cosine of theta plus sine of theta all over sine theta cosine theta. So being able to add two trig functions together, get a common denominator. Alright, if this is confusing you, think of what if you had to add like 1/2 plus 1/7. Okay, you'd have to get the common denominator of 14. And how did you get the common denominator of 14? You have to multiply 2 times 7, right? So that gave you the 14. So then you had to multiply the 1/2 by 7 over 7, right? So you got 7 halves, and then you had to multiply the 1 over 7 by 2 over 2, all right, to get 2 over 14. So you had 9 over 14 is your answer, okay? So same kind of concept there, only we're doing it with a trig function. All right, make sure that you're not changing something when you're doing your substitution that doesn't meet the end goal. So you're looking to get something in terms of sine and cosine. Don't do a substitution that's going to only leave it in like a cotangent or something like that. Okay, so if we want to do and we're looking at this example here, we have tangent squared x plus 1 is equal to 1 over cosine squared x. We want to find the identity that relates tangent and cosine. Alright, so for that one's pretty simple though. It's a Pythagorean, right? We would recognize that we would use secant squared. Alright, because secant is the inverse function of cosine. And since we already have 1 over cosine, it's actually 1 over cosine squared of x, we can translate that into secant squared of x. And then obviously it's equivalent to the Pythagorean. Alright, if we have an expression that contains 1 plus sine of x, you got to multiply both the numerator and the denominator by its conjugate. 1 minus sine x. Okay, what's the difference between 1 plus sine x and 1 minus sine x? The sign, right? One is plus, one is minus. That's called the conjugate. Later on we'll get into what a complex conjugate is when we do complex numbers, and you might have heard of it there, but we're going to multiply by the conjugate. Okay, and why would we do that? So we get 1 minus sine squared. That's easily replaceable with cosine squared. How is it? Break down the Pythagorean identity of sine squared plus cosine squared. Solve that algebraically for cosine squared, and you get 1 minus sine squared x. Okay, so that is a rule that's really going to help us do some simple substitution. Okay, we can do the same thing for 1 minus sine of x, 1 plus cosine of x, and 1 minus cosine of x. Just remember, when we're verifying identities, we're not solving equations. So what that means is we're not moving stuff from one side of the equal sign to the other. We're either attacking the left side of the equal sign or we're attacking the right side of the equal sign, but we're not solving for a variable. We're not trying to get all the variables on one side and all the constants on the other. We don't do that when we verify an identity. We want to make one side look like the other. When I say side, I mean the equal sign. Alright, so you're not solving for anything, you're verifying that one is equivalent to the other. Alright, so we're going to go through different techniques here when we do this, okay? Sometimes, okay, the best approach is for you to just only look at one side of the equal sign. Okay, only look at one side of the equal sign and work with it, and always pick the most complicated side. Alright, so let's take a look at an example here. We want to verify the following equation is an identity. So we want to make sure that we can say that cotangent of theta plus 1 is equivalent to cosecant of theta times the quantity of cosine of theta plus sine of theta. Alright, now in your head, which side's the most complicated side, or which side's got more going on? The right hand side. That's the one we're going to simplify, because remember, it's easy to go from complicated to simple. It's hard to go from simple to complicated. So we are going to leave the left hand side of the equal side alone, or the equal sign alone. It's going to stay over there and it's going to say cotangent of theta plus 1. We are going to work through properties or identities to make the right hand side of the equal sign look like the left hand side. Okay, so you know, there are a couple different ways here. You could start either by rewriting cosecant of theta as 1 over sine of theta, or you could distribute the cosecant first and use the distributive property. So distribute the cosecant to cosine and distribute the cosecant to sine. Okay, so either or works. Now the best method I would say is always try to turn everything into sine and cosine. So we're leaving the left hand side of the equal sign alone. We're only working with the right hand side. Okay, so rewrite cosecant of theta as 1 over sine of theta. Then distribute it through. When you distribute it through, notice we're going to get 1 over sine theta times cosine of theta and 1 over sine theta times sine of theta. So when this simplifies down, we end up with cosine of theta over sine of theta plus sine of theta over sine of theta. Well, sine of theta over sine of theta simplifies. Anything over itself is always 1. And we should also note that cosine of theta over sine of theta, okay, is another way to rewrite cotangent of theta. So cosine of theta over sine of theta is easily rewritable as cotangent of theta, okay, plus 1, because sine of theta over sine of theta went to 1. Now we have made the right-hand side of the equation look exactly like the left-hand side of the equation. Okay, so breathe a little. I know that these are going to be a little scary, but they will come natural to you, and you will be able to work through them. You just got to be patient, all right, and have your identities with you. All right, so we want to verify the following equations in identity. We have tangent squared of x times the quantity of 1 plus cotangent squared of x equals 1 over 1 minus sine squared of x. Okay, so you got to think about, hey, which one's the most complicated side? Obviously the left-hand side, because we got the distributive property going on. and some addition going on. So there's just more to do. Okay, so what I would do first is distribute it. So distribute the tangent squared x to the 1 plus cotangent squared x. When you do that, you're going to get tangent squared x plus tangent squared x cotangent x. Okay, so now when we take a look at that, what can we do? We're going to rewrite cotangent squared of x. That's really going to help us out here because, all right, when we multiply tangent squared of x times 1 over tangent squared of x, it ends up becoming 1. Very crucial for us. But you need to recognize that. You need to always looking to cancel stuff out. Oh, cotangent and tangent. All right, they're inverses of each other, so if they're multiplying, it's just 1. Okay, or just rewrite them if you need to. So we're left with tangent squared x plus 1. Now, that's easily rewritable, okay, into secant squared of x. Okay, we're getting there. Are we there yet? What do we have to make the left-hand side look like? It's got to look like 1 over 1 minus sine squared x. Well, you're like, well, we're at secant squared x. All right, how do I rewrite secant squared in terms of cosine? All right, it's the inverse property. It's 1 over cosine squared. We were like, well, how did that help me? This is where you need to understand and have the Pythagorean identities rewritten. You should have the Pythagorean identity written 3 different ways. The first way is sine squared plus cosine squared equals 1. The second way is sine squared minus cosine, or sine squared is equal to 1 minus cosine squared. You should also have cosine squared is equal to 1 minus sine squared. Okay? So sine squared is 1 minus cosine squared is 1 minus sine squared. Well, that's very important. Cosine squared of x, using the Pythagorean identity and solving the Pythagorean identity of sine squared plus cosine squared x equals 1. If we solved that for cosine squared of x, we would get 1 minus sine squared. So we can replace the denominator of 1 over cosine squared x, the denominator is cosine squared x, we can replace that with 1 minus sine squared because we've solved the Pythagorean identity in terms of cosine. So you got to think about these procedures and you got to think about all the different ways that we can write these identities out. Okay, these just take practice. I know they're confusing, all right, but practice. So maybe, pull this one aside and rework it on your own. Pause the video, rework it, and then double check yourself. See if you're able to duplicate all these steps on your own. All right, so let's do this one. We want to verify that tangent of t minus cotangent of t all over sine of t cosine of t is equal to secant squared of t minus cosecant squared of t. We want to prove that it's an identity. So what we got to do, all right, is pick the more complicated side. Okay, the more complicated side is the left-hand side, all right, because we have a common denominator and we got some things mixed and match. One rule of algebra, okay, and it's over there on the left-hand side in blue. A minus b over c is equivalent to a over c minus b over c. When you have a numerator that is separated by addition or subtraction over a common denominator, you can rewrite those as 2 separate fractions. Okay, so you're able to rewrite it as 2 separate fractions. So our tangent of t minus cotangent of t all over sine of t cosine of t can rewrite as tangent of t over sine of t cosine of t minus cotangent of t over sine of t cosine of t. Okay, very, very, very important rule that you guys do that. Alright, so make sure that you pay attention, and it's got the basic piece over there in the blue on the right hand side. So what you need to do is kind of factor out the tangent and cotangent, because we're going to rewrite tangent and cotangent in terms of sine and cosine. Well, why? Because that's going to help us do some canceling. If I rewrite tangent as sine of t over cosine of t times 1 over sine of t cosine of t, the sines are going to cancel and I'm going to get 1 over cosine of t. Okay? And then after the minus sign, if I rewrite cotangent of t as cosine of t over sine of t, times 1 over sine of t cosine of t. The cosines will cancel, and I'll be left with 1 over sine squared of t. Alright, don't jump the gun here. Don't think, oh, I got the Pythagorean, I can cancel right away. You gotta be careful, because that's not the goal. The goal was to make the left-hand side look like the right-hand side. So we're one step away. We just need to use the inverse identities. 1 over cosine squared t translates to secant squared of t. Okay, 1 over sine squared t translates into cosecant squared of t. So we're one step away using the inverse identities, and now we have made the left-hand side look exactly like the right-hand side, and we verified the identity. Alright, let's do another one here. This one might be a little more complicated to choose, which side's going to be the hard side. So we're going to verify that cosine of x over 1 minus sine of x equals 1 plus sine of x over cosine of x. It's one of those where, which one? I would say, sometimes, usually the one with the more complicated, denominator, sometimes you choose. But if you remember the rule before, where I talked about using the conjugate, sometimes we can choose the one that has, you could do the conjugate rule here either way, to the left-hand side or the right-hand side. Alright, but sometimes it's easier because that's already in the numerator. So we're going to work with the right-hand side and make the right-hand side look like the left-hand side. Okay, so in order for us to do that, we're going to multiply the right-hand side by the conjugate, which is 1 minus sine of x. Okay, what we have to do to the numerator, we do to the denominator, because we're multiplying in the form of 1, but it's in the form of 1 minus sine of x over 1 minus sine of x. Okay, so that's the conjugate rule that I talked about towards the beginning of the lecture. When we do this, okay, on top, okay, you got a FOIL. So you're going to FOIL the top, and then see what happens first. Don't necessarily distribute the cosine of x in the denominator to the 1 minus sine of x, because the left-hand side already has a 1 minus sine of x in the denominator. You don't want to delete it or cancel it out. When we FOIL the top out, we end up with 1 minus sine squared of x. I'm saying FOIL, you may not all know FOIL, or the box method, or binomial multiplication, however you were taught to learn that one. Alright, so in the top we have 1 minus sine squared x. If you remember, we can rewrite the Pythagorean identity and replace 1 minus sine squared x with cosine squared of x. Okay, rewriting the Pythagorean identity and solving it for cosine squared of x. Now what do we get? I have a cosine squared over a cosine. So I have cosine squared x over cosine of x. Well, the one in the denominator is going to cancel with one of the squares. Alright, it's kind of like having x squared over x, right? I'm left with x. We're doing the same thing only with cosine. So we'll have one in the numerator, alright, and the one in the denominator will cancel out. So we're left with cosine of x over 1 minus sine of x. And we are done. We have made the right-hand side look exactly like the left-hand side. Now you could have reworked this problem the other way. You could have attacked the left-hand side and used the conjugate of 1 plus sine of x over 1 plus sine of x and done all the same work and gotten there the same way. Okay? So we want to identify or verify the identity. Okay, works both ways. Okay, so each step on each side has to be reversible. Okay, and we want to look for a common third expression. This is only where it gets like super challenging. Looking at this example, it's somewhat of a toss-up. Which side's more complicated? Alright, we got secant of alpha plus tangent of alpha all over secant of alpha minus tangent of alpha on the left, and then on the right we got 1 plus 2 sine alpha plus sine squared alpha. Right, we can rewrite that though as 1 plus sine alpha squared over cosine squared alpha. So we got to be careful here how we're going to work this. So we're going to work with the left-hand side first. Okay, we're going to multiply by cosine of alpha over cosine of alpha. And you ask, why do we choose cosine? Well, it'll help cancel, because what's secant the inverse of? Cosine. Alright? So since secant is the inverse of cosine, I'll be able to cancel out the cosines. So that's why I'm choosing cosine of alpha. So we're going to multiply by cosine of alpha over cosine of alpha. That's also going to help because tangent is what? Sine over cosine. So when we do that, we're going to get some cancellations. So we distribute cosine of alpha to the numerator and we distribute cosine alpha to the denominator. Alright? Once we do that, we rewrite everything. Okay? So rewriting secant as what? 1 over cosine. And 1 over cosine times cosine is 1. So that's where the 1 comes from. Okay? Or on the right hand side in the blue note, I have secant of alpha, cosine of alpha. Since their inverses multiplying each other, they equal 1. And then we're left with sine of alpha over cosine of alpha times cosine of alpha. Alright, where did the sine of alpha over cosine of alpha come from? That's rewriting tangent. Okay, and then those cosines of alpha will cancel. In the denominator, same concept. We have secant alpha, cosine of alpha. Those become 1 minus rewriting tangent of alpha as sine of alpha over cosine of alpha times cosine of alpha. So the cosines are all going to cancel. So I'm going to be left with 1 plus sine of alpha over 1 minus sine of alpha. And this is where we're verifying both sides. So we're going to leave the left-hand side alone now. And we're going to say the left-hand side can simplify down into 1 plus sine of alpha divided by 1 minus sine of alpha. There's not a whole lot else we can really do other than maybe multiply by the conjugate, okay, and see where that gets us. So let's go to working on the right-hand side. So we're still on the same problem here. We're going to do some work on the right-hand side. So as long as I've done some work on the left-hand side, we're going to make the right-hand side of the equal sign look similar. Okay, so like I said before, we can factor the numerator. So 1 plus 2 sine of alpha plus sine squared of alpha translates into 1 plus sine of alpha quantity squared. You guys, that's no different than if you have 1 plus 2x plus x squared. Okay, you're just factoring it out. So it's a binomial squared. Okay, over cosine squared of alpha. So we can rewrite the denominator as 1 minus sine squared alpha. Okay, that's using the Pythagorean identity and rewriting it in terms of cosine squared alpha. Okay, then what we're going to do is we have 1 minus sine squared alpha. Remember, that's the difference of two perfect squares. Alright, a perfect square is 1 and a perfect square is sine squared. So it's the difference, so that's why it's 1 plus sine of alpha times the quantity of 1 minus the sine of alpha in the denominator. Okay, we didn't touch the numerator. Remember the difference of two squares? If you had like x squared minus 36, right? It was x plus 6 times x minus 6, so the 0 term cancels out. Same concept here. Alright, so when we simplify this out, alright, we have a 1 plus sine of alpha squared in the numerator, and we have a 1 plus sine of alpha in the denominator. Okay, the one in the denominator cancels out, and you're left with one of those in the numerator. So we can say that the right-hand side also simplified to 1 plus sine of alpha over 1 minus sine of alpha. So now we can show that the left-hand side is indeed equivalent to the right-hand side, because the left-hand side we were able to get a common third expression. Alright, whether we worked down through the left-hand side and we worked down through the right-hand side, and we got that common middle expression right there. Okay, so that's about as challenging as those are going to get. Alright, so let's do something more real-world-esque. Alright, so we're going to use the Pythagorean identity in electronics. So I'll read the problem here and then we'll work through it. Alright, tuners in radios select a radio station by adjusting the frequency. Alright, so a tuner may contain an inductor and a capacitor. Alright, just for reference, I'll show you guys what those look like in class. But an inductor is literally a coil of wire that stores a magnetic field, alright, and filters certain signals. A capacitor stores an electric charge. Alright, it helps filter signals as well, so we use what we call an RLC circuit, a resistor capacitor inductor circuit, to actually fine tune to like different radio stations. So if you listen to 101.5, all right, remember that was FM frequency modulation, so the frequency that we talked about when we were graphing. All right, same concept here, you tune in to a certain frequency. All right, so we store energy in inductors and capacitors. So in an inductor, that's the one with the L, all right, the coil of wire, the energy is stored as L of t is equal to K sine squared times 2 pi f t. All right, and the energy in the capacitor, C of t, is K cosine squared of 2 pi f t. All right, now F is the frequency of the radio station, and K is a constant, okay, that's going to be given to you. So let's work through a problem here. So we want to find the total energy in a circuit is by doing what? Adding the energy in an inductor plus a capacitor. Alright, so for those of you guys that aren't in engineering or aren't in mechatronics with us, alright, this is a simple circuit here. Alright, the symbol on the left, L, is what an inductor symbol looks like. That's how we represent an inductor. The symbol on the right with the two bars is how we symbolize a capacitor. Alright, so the total energy is the inductor's energy plus the capacitor's energy when we do this. So we substitute in the two equations. So L of t's equation is K sine squared times 2 pi f t plus the capacitance, K cosine squared 2 pi f t. So we factor out a K, it's common to both of them. Alright, and we can take K times 1, and we can say what? And this is what's very crucial here and what makes it easy. K times 1. Well, we notice that what? We have sine squared of 2 pi f t, and we have cosine squared of 2 pi f t. Anytime we have sine squared of something plus cosine squared of something, we can always rewrite it as 1. That's what's awesome. As long as the argument is the same for sine and cosine. The argument being what's in the parentheses, which is 2 pi f t. Okay, so we can rewrite that entire thing, sine squared plus cosine squared, as 1. Okay, very, very cool. So the total energy is just K times 1. So E of t is literally just K. That's the total energy in that circuit. So since K is a constant, energy is also a constant function. So there's where we would use something like that in a real life problem. So we won't do anything with the frequency and time calculations, but there's a lot more that kind of goes into it, but it's just a way for you to see and understand how we can apply, you know, a trig identity, the Pythagorean identity, to a real world problem. Alright, so that's it for section 2. You got questions, go ahead and email me. Alright, you should have questions in this section. Alright, I just want you to know this is one of the more challenging sections in the book. Just getting used to it. Alright, it's not as hard as doing geometry proofs or things like that, but you just got to be able to see and recognize and have some sort of methodical approach to it. Make sure that you have your trig cheat sheet sitting there next to you so that you can look at all the identities to help guide you through how to simplify these. Okay? So once again, email me. Let me know if you need extra help on a certain problem or anything along those lines. Else, the rest of you guys, I will see you in class.